Thank you very much for having me. Can I be heard all right? Yeah, okay, yeah. Thanks a lot for the invitation. And this is my third time giving a talk in this department in the last a little more than 20 years. Every time I came to Seattle, the weather is fantastic. So I always wonder, where is this rain everybody's talking about? Okay, but anyway, it's great being here. And also I enjoy your new building next door. So I'm going to talk about statistical neuroimaging analysis today in a way that I'm trying to give an overview of some of the stuff we have been working on. I was just told I have 90 minutes. All of a sudden I feel so good, so much time. I won't use all the time. Anyway, during the talk, if you have any questions, feel free to stop me. Happy to answer all the questions. So here's the outline. I will begin with an quick overview, and then I'm going to go through a few examples, case studies. And then towards the very end, I will just briefly mention some additional projects our group has been working on. Given the time limit, I still try to get everything done within about an hour. And I probably won't be able to go into a lot of technical details. Actually, all these examples or these works have already been published. So if you are interested, I'm more than happy to direct you to the papers, and I'd be happy to talk about some of the details. What I'm going to do in the talk is trying to give some high-level description and introduction, what the problem is, why we are interested in this kind of problem, and how we approach this problem or formulate the problem, and then a little bit of our main ideas. But then I will skip quite a bit of technical details. With that said, again, if you have any questions, feel free to stop me. I'd like to thank my funding support and my long-term neuroscience collaborator, Dr. William Jacobs from Berkeley. And also these different projects are usually joint works with different groups, Jingfei Zhang and Emory, Wilson and Purdue, and Xiao Wudai and UCLA now, and Chen Chen and London School of Economics. So let me begin by saying that neuroimaging is a very exciting area for multiple reasons. First of all, understanding how human brain works is always a very exciting, fascinating topic. We try to understand how the brain normally develop from children and to this old age. And we are very interested in different types of neurological disorders. One particular disorder our group has been working a lot on this Alzheimer's disease, which has a lot of interest nowadays. And then also like attention deficit hyperactivity disorder, autism, Parkinson's disease, and some other disorders. More recently, we start to look at this interaction between human brain and computer. So this brain-computer interface is also one of the very intriguing questions. Statistically, neuroimaging really is just a very broad area that covers many different types of statistical problems, models as well, not just one family of statistical models or one family of statistical solutions. It covers quite a bit. Actually, in a couple of slides, I'm going to give you a quick overview of some of the topics we have been working on, and you can kind of get some rough sense, how diverse those different problems could be. Okay. The classical neuroimaging data sets are relatively small, and this is not surprising. It's not easy. It's expensive to collect MRI, fMRI data, neuroimaging data in general. But the good news is in the past few years, there are a few or more and more large public databases are becoming available about neuroimaging studies, which in effect allows us to do something a little bit more sophisticated. Okay. Finally, there's some personal interest on this. Ever since I started to work on this direction of neuroimaging, neuroscience, a lot of my friends, even my in-laws, got interested in what I'm doing now. Okay, so I feel good. So we really work with different types of images, or we call them imaging modalities, like anatomic MRI, functional MRI, PET, EEG, ECOG, DTI, also as neuron labels like neurospectrin type of data. Just different types of images. We work on all sorts of those images. There are some common challenges. The dimensionality is always a challenge here, but on top of that, we also have to deal with complex spatial and temporal correlations. The associations between the images and the, say, clinical outcomes, as well as these associations between different types of images, are generally very complex. Linear model may be a good starting point, but often inadequate to characterize these complex associations. I already mentioned the sample size is forever an issue. Even with availability of some large, relatively large imaging database, it's still very small. Of course, it depends on what kind of standard. But for instance, if you want to apply some deep neural networks model to imaging data, it's not an easy task because unlike natural images where we can easily find tens of thousands or millions of pictures of natural images like cats, dogs, horses, and so on, much smaller sample size for human brain image data. A ton of confounding variables, and if you work with longitudinal images, many missing values, and also a lot of subject domain knowledge we want to incorporate. So these are just some of the common challenges we are facing, no matter what kind of image type we are working with. And so what our group wants to do is to try to hopefully find some ways to deal with some of those challenges. We want to be able to come up with reasonably flexible estimation methods, as well as rigorous statistical inference tools. So statistical inference is something we value a lot. We want to be able to achieve as well. Then along the way, the interpretability is another thing we really care about, because at the end of the day, what we really want to achieve is to gain some better insight of, again, how brain works, how things look are different in terms of neurological disorders, why this kind of a difference, those kind of questions. And finally, we hope we could also contribute a little bit to the statistical theory and the methodology development. So as I mentioned earlier, our group really works on a wide variety of neuroimaging problems. Actually, I've been working in this area in the past 10 years or so. So like when we started working on neuroimaging tensor analysis, where we treat image data either as a matrix or a three-dimensional array, sometimes higher dimensional array. And we want to understand questions like, for instance, how to predict a clinical outcome given the observed images. For instance, this can be very useful in early diagnosis for Alzheimer's disease. We also want to answer questions like how brain images look different between different groups of patients. This is a typical problem in statistics, right? Or also in computational biology, where we want to find, for instance, the differentially expressed genes. Here, what we are looking for is sort of differentially expressed, I use this word in a loose way, brains. I have a group of patients with some disorder. We have a group of normal control or normal developing brains. I want to find out where the difference is. Another family or category of problems we are working on is so-called brain connectivity network analysis. So this tensor analysis really focuses on the questions like what brain regions do what, or what brain regions become different. The second family of questions is brain network analysis, really look for the interactions and connections between different parts of the brain regions. So in neuroscience field, neuroscientists are very excited about this brain network analysis. So we want to understand how different parts of the brain they communicate and collaborate with each other. And also we want to understand how such network patterns are related with some, say, clinical outcomes. So these are the questions we are interested in, and we develop some, a bunch of graph theory-based models, methods for this family of problems. And then comes this multimodal neuroimaging analysis, which again, intuitively, I think makes a lot of sense because nowadays it's relatively easy for us to collect different types of images from the same group of patients. And intuitively, each type, anatomic MRI or functional MRI, could tell us some useful information about the brain. So they probably provide some complementary information about the brain. Therefore, how to jointly integrate those different types of images, different types of brain information is the question we are targeting over here. And now causal inference is forever a question of a lot of interest. Here, of course, we have to use this word causal a little bit carefully. What we are looking at are some specific problems somewhat related to causal inference. So one family of problems we are studying is association, mediation analysis. This is actually one of the case studies I'm going to talk about later today. Another family of problems we are looking at under this part is about directed graph or DAG. So we want to estimate and to infer, to estimate and inference about the DAG directed networks. Finally, there are new imaging modalities, new imaging technologies coming out all the time, depending on the type of the images or the type of or the features of the data. It requires all these different tools. Like we use a lot of functional data analysis FDA approach to look at our imaging data. More recently, we are studying ordinary differential equations to model some type of imaging data, point process modeling. The last two pieces are something I'm working on very recently, right now actually, deep brain stimulation and brain-computer interface. So I don't have much results to show you today, but I just briefly mention, like for instance, deep brain stimulation is some very cool technology. That is something we are working on. Is we open up the skull of the patient and we insert the electrodes, and then we can stimulate the brain. And right now we are targeting Parkinson's disease patients, but this technology, this actually treatment, is being applied to a wide variety of neurological disorders, as well as to the normal people. That's what Elon Musk is doing. One of his companies, Neuralink, is essentially doing something like that. So we insert the electrodes, we stimulate the brain, and we see the reaction of the brain. There is strong belief this kind of stimulation would help the patient, like in the context, for instance, Parkinson's disease. But then why this question is interesting to us, what we used to do for this deep brain stimulation, we did it in a fixed way. So it's like we see a doctor, the doctor prescribed saying, oh, you should stimulate your brain with this magnitude, this amplitude for this much time. Everything was more or less fixed until the next physician visit. Nowadays, we want to do it in an adaptive way because we have these devices, these technologies, like we have Apple Watch, for instance, to collect the real-time reaction, real-time data from the patient. So intuitively, if the patient is in a bad state, then we probably should stimulate more. If the patient is in a good state, then we probably should stimulate less, maybe smaller amplitude, less time. So how to do this deep brain stimulation in an adaptive way? One way to formulate the problem, this is the reinforcement learning kind of problem. So we are building some reinforcement learning based strategies for this kind of problem. Okay. So here again, I just want to use this slide to show you neuroimaging really is a collection of a diverse range of different problems. So a lot of those are very different, but also very exciting. So what I'm going to do is I'm going to go through a few examples. I call them case studies. Again, I hope I could give you a little bit of taste of some of the problems we have been looking at. The first one is this dynamic or time-varying brain connectivity analysis or brain network analysis. Okay, so I already mentioned in neuroscience community, there is a lot of interest in understanding how brain network works. So a type of brain network we were looking at is so-called functional brain functional connectivity, which essentially reviews the synchronization of different parts of the brain systems through the correlations in neurophysiological measures of the brain connectivities. During the resting state, we believe this kind of functional connectivity tells us useful information about the intrinsic functional architecture of the brain. And we also found that, for people with certain disorders, the connectivity network changes substantially. Therefore, we believe this kind of functional network also holds useful insight about the neurological disorders. The study we were looking at was from this ADHD, where we look at close to 500 healthy subjects. So this is part of the ADHD study, not the complete study, but a part of it. These about 500 healthy subjects, aging between 7 years to 20 years old. Each subject, we collected a resting state functional MRI. So fMRI essentially measures the blood oxygen level over time, and we use this blood oxygen level as a surrogate measure of the brain neural activity. So the original data of fMRI comes in this 4-dimensional array, 3 spatial dimensions plus a temporal dimension. It's quite common to collapse the 3 spatial dimensions just to make the data a little bit more tractable, easier to handle. You don't have to, but this is a common practice. So for each subject, we first of all map the brain voxels to a list of pre-specified brain regions. We call those atlas, brain atlas. And then we average the time course data of the voxels within each brain region. So we end up having brain region by time matrix for each individual person over here. So the brain atlas we use has 264 brain regions. So this is a typical number. And there are different brain atlas to use, but the number of brain regions of interest we often use range from about 100 to 300. So 264, this is a typical number. On top of that, we also have some additional piece of information telling us those 264 regions can be further partitioned into 10 functional modules. So what is a functional module? So one way to think of it is like functional module is a collection of brain regions that tend to work together. Okay, so we have this additional piece of information which we will utilize later in our modeling. So we very naturally we use graph model or this graph representation to model this kind of data. So for each individual patient, we build an estimate of the graph or network, and this graph, this network, each individual node represents one of the brain regions. So I have 264 nodes. The link here essentially measures a pairwise correlation, pairwise dependency between those different brain regions. And there are different correlation measures. There are actually more than one correlation measures, like Pearson correlation, partial correlation, mutual information, so on and so forth. Here, our interest for this particular study was not trying to compare different metrics over here. Instead, we just use a common metric, that is a partial correlation. We further diagonalize the partial correlation between each pair of the brain regions to 0, 1, just to, again, simplify the analysis a little bit. So you can imagine each patient has a 264 by 264 network representation, network measure. Each link either 0 or 1. If there is 1, that means we believe there is some functional connectivity between that particular pair of brain regions. Okay. What we are particularly interested in this study was we want to model the dynamic patterns, dynamic behaviors of these brain functional networks with respect to age. In other words, when someone grows up in our data from 7 years old to about 20 years old, we want to model how these brain network patterns change over time. So this was actually a project we did a few years ago. At that time, most of the literature focused on static network. We are more interested in a dynamic network modeling problem. There were a few papers looking at dynamic networks at that moment, but the number of time points were quite small, usually 2 or 3 time points, but we were more interested in a continuous time. So this connectivity network pattern, we want to model it as a continuous function of the time. Finally, there is one more interesting difference is a lot of classical network models, so graph theory-based models, only work with a single graph, single network. What we were working with are multiple networks. Essentially, each individual patient, we have a network representation. So we can think of this as we have a population of networks. That is something we are interested in. But each individual patient, we observe a single realization of this population. Okay, so this idea is not uncommon for statisticians at all, but we typically work with single random quantity or vector of random quantities. But here we just replace that with a network. We have the population of networks. Each individual has one single realization of this population of network. Okay, so here we use this kind of notations to model the data. Here is our main idea. Actually, I'm just going to use like 2 slides to summarize our main idea. Oh, please. Sure. Okay. Yeah. Okay. Good question. So again, in this specific example, we have about 500 subjects. Each subject, we can construct this 264 by 264 network. Then when we say we want to understand the dynamic behaviors, there is actually the second temporal dimension coming in. That is the age. So we want to see when someone grows up, how this network varies. Yes, exactly. So when I say this slide, I have each subject, I have multiple time points. Yeah, the time means age. But the fMRI data itself also has a temporal dimension, but that is a different temporal resolution. So fMRI data, essentially, you can think of it as MRI images collected very, very quickly over time. But the temporal dimension for fMRI data usually is 500 milliseconds to 2 seconds. So it's very, very short time. But actually, later I'm going to look at another case study, even shorter. But fMRI, 500 milliseconds to 2 seconds. We turn that temporal dimension into this estimation when I construct this 264 by 264 network. So the second temporal dimension is something I'm more interested in here when I talk about dynamic modeling. That is the age, basically, which is, of course, a much sort of a wider temporal scale here. Okay, so this is the main idea. The key idea is essentially we borrow this, stochastic block model. And instead of working with 264 networks, we say, we do have this additional piece of information saying those brain regions belong to different functional modules. So we treat those functional modules as individual communities. And then we naturally use this stochastic block model. So if you are familiar with a stochastic block model, this first line of equation should look very familiar, just classical stochastic block model, which says the connectivity, okay, for subject I between 2 individual nodes in this network, depending on which 2 communities or which 2 functional modules these 2 nodes come from, follows a Bernoulli distribution with this probability. What we add on top of this classical stochastic block model is this probability. We are going to model it in this specific way. It is essentially the summation of 2 components. The first one is a connectivity function that tells me what's the population level connectivity between any 2 functional modules. Okay, and then the second component is a random effect term that accounts for subject level variation. Now, this second term is quite important. Again, this I indicates individual subject I, because we know in neuroimaging data and also especially in functional MRI data, there is quite a lot of subject-specific variation. So it's kind of important to take into this account in our model. And so the second term is essentially a random effect term. So we model this random effect term using a normal distribution, which has this variance function. Now, both this connectivity functions, this theta and this variance function sigma, are functions of this continuous time variable, in other words, age over here. So we want to model these two key pieces or key components as a continuous function of time or age over here. Some of you may notice that I do have subscript KL. Again, this means module K, module L. So for each pair of functional modules, I allow this connectivity function to be different in principle. The variance, I drop this subscript, meaning that I'm forcing them to be all the same. Now, this is just a typical trade-off. It could be different, but then that means I have more free parameters to estimate. Here we just do a compromise. A few more quick remarks in our model. One is right now, we model this Bernoulli probability through a known link function as a summation of these two components. We have not yet incorporated the subject-specific covariates, but this can be incorporated very, very easily. For instance, if somehow we believe these network trajectories, these patterns are different between boys and girls, then we can add this gender as one of the subject label covariates. If we have some other covariates to include, that can be incorporated very, very easily. Another remark here is we use this stochastic block model. We treat each functional module as a block, as a given known information. And during this dynamic change, we assume these connecting probabilities may change over time, but we assume this functional module information stay the same. Okay, now this is sort of makes sense in this context of functional module neuroimaging. That this functional module are essentially some years of empirical knowledge, empirical evidence showing that different parts of brain they do tend to work very closely to each other. Like one functional module, very famous, is default mode network. Okay, so we assume this kind of functional module information stay the same. Of course, from the modeling perspective, from the methodology perspective, we could make this model a little bit more complicated by allowing this functional module part to change over time or over age as well. Okay, but in this particular study, we keep it relatively simple. And then this is basically essentially our main idea. And then we did a few more things, how to model these two time-varying functions, this connectivity function theta here, and also this variance function sigma over here. We use piecewise constant functions. Now, again, there are a number of advantages of doing that by using piecewise constant function. First of all, we find that sort of agrees with empirical evidence in brain development studies that the development brain or brain often goes through a mix of periods of rapid growth and then plateaus. It may go up very quickly or change very quickly and stay stable for a while, and then another period of quick change and stable, something like that. So to capture this kind of pattern, piecewise constant function seems to be a reasonable choice. And of course, also this piecewise constant function allows the interpretation much easier and allows us to pull the information together for those subjects with similar ages to estimate the unknown parameters. Okay, so that's the main ideas. Please. Sure. Okay. Yeah. Again, here we did do a little bit of simplification. And this 264 by 264 network. If we use partial correlation, you are right. It's essentially some kind of continuous value network. But in reality, most of the time, the neuroscientists are very interested in this. If there is a connection or not, or no connection. So that's why we kind of do this simplification. Yeah, but and this also, of course, allows us to just easily use the stochastic block model. we could look at the continuous work for sure. Yeah. So yeah, good question. So we did do quite a few sort of simplifications over here to essentially some trade-off in terms of model feasibility and the the interpretation and so on. But we try also at the same time try to make sure these simplifications are reasonable in this particular context.
When you threshold the partial correlations, when you do it negative partial correlations, are you thresholding the absolute values? Okay, so these could be connections that could be excitatory or induced, and they're being treated sort of the same.
Absolutely, yeah. So again, I totally agree. This is kind of a simplification over here. Yeah. Yes, please.
I'm curious how similar networks look.
Yeah. So again, yeah. The brain network could differ quite a lot from subject to subject. That's part of the motivation that we really want to include this random effect term over here. But with that said, we still somehow believe maybe for the patients with this ADHD, for instance, or Alzheimer's disease, there is still something in common in terms of network behavior. So if you think of this everything as coming from this population of network, so we still somehow believe maybe there is some common mean behavior, average behavior for the patients from the disorder group, and there is another population mean for the normal developing patients. But on top of that, there could be a lot of variability, so the variance term could be large.
Yeah, I guess I was just wondering, do you have any sort of summary of how similar?
Oh, yeah. In this study, we didn't particularly looking at that, but there have been a lot of other studies sort of showing this kind of patterns seem to be reasonable. That's why, a lot of studies, including some of my own studies, not talk about here, but we did in some other papers, we were just comparing, say, two groups of brain networks and do some testing, see how different or how similar they are in different parts of the brain. Yeah, those are good questions. Thanks. So back to this, this is essentially our main idea. But then, of course, on top of that, we did a few more technical stuff, like we developed a maximum likelihood estimation procedure using some integration, numerical integration. We added that shape constraint to further improve the estimate to improve the interpretability. We also add some fusion constraint, essentially some kind of smoothness and sparsity constraint. And we study some theoretical properties like estimation error rate, the asymptotical recovery guarantee, and those kind of things. So I'm not going to go into those technical details, but I'm just going to show you some numerical results. So this is our motivating example. And on this slide, I'm showing this estimated heat maps of the estimated connecting probabilities at different age. So the age what we observe is a little bit continuous from 7 years old all the way to 20, but we group those by this age 8, 9, and so on. So first of all, we see that the diagonal elements here have darker colors than off diagonals. So what that means? That means the estimated connecting probabilities for those within community connections are indeed stronger than the between community connecting probabilities. So again, this function within this community or functional module is some prior knowledge, domain knowledge we utilize, we treat it as known information, but it seems to be supported by the actual data. So this data did find that those within community or within functional module connections are stronger than the between community connections. Okay. The second finding we found from this estimation is that if you see someone, as someone grows older, the off diagonals have stronger and stronger connection probabilities. Also sort of makes sense. So when we grow older, seems that our different parts of brain, different modules of brain also learn to coordinate, to collaborate more and more together with each other. And then this second plot shows just the within community connecting probability, but this time we plot this estimate as a function of age, function of time. So on the horizontal axis, just the age. We see that other than one particular functional module, which is the cerebellum, or other functional modules, as age increase, the within community connectivities tend to increase. And then there are a few clear jump points. Those are the ages where we identified, we noted a lot of changes, quite substantial changes in terms of the within community connecting probabilities. Okay, so one is around age 9 and 10, that corresponds to late childhood and early adolescence. And then another is age 13. That is where the teen age starts. Okay, and I have a daughter who just entered the teenager years. This sort of finding supports all of a sudden why her behaviors change quite a bit nowadays. Anyway, so this is the first example, please. This one, or one more, or this one. Those are 10 functional modules. Yeah, so I have 10 functional modules. So this each small square means the within connecting probability within functional module 1, within functional module 2, and so on. And these squares, off diagonal squares, means between community connecting probabilities. Yeah. I don't remember exactly how these 10 functional modules were defined in terms of the hemispheres. There is some symmetry between left and right hemispheres, but not completely symmetric either. So what I remember now is we look at these 10 functional modules. Again, this is a given information, but I think maybe some functional modules come from some hemisphere, but not necessarily 1 to 5 from left or 6 to 10 from right. Probably not like that. Yeah. Okay. So this is the first study. Then I move on to the second example. Now, second example, we are going to switch gear. We are going to look at a very different problem. This is about ordinary differential equation modeling. Now, here's our motivation. We are still looking at the connectivity analysis in the brain, but this time we look at the so-called effective connectivity analysis. By the way, these terms like functional connectivity, effective connectivity, these are the terms developed by the neuroscientists. We sort of just borrow those terms. But what does the effective connectivity means? It means we want to understand how one part of the brain or one brain system influence another brain system. Okay, so this brain system could be one particular brain region, or could be a functional module, or could be individual neurons as well. The main difference between effective connectivity and the functional connectivity I was talking about earlier was that in effective connectivity, we also care about the directions, because this is like one area, one region affects the other region. This relation is not always symmetric. So there is direction. By contrast, functional connectivity, we focus on this undirected network. It's just some kind of correlation, some type of correlation. So it's symmetric for the functional connectivity, asymmetric for effective connectivity analysis. Okay. And the particular imaging modality we are looking at is this ECOG data. Now, ECOG data is kind of an invasive imaging technology, typically requires the insertion of the electrodes inside the brain. So we do need to open up the brain, insert the electrodes to collect very high quality of brain activity data using this ECOG study, ECOG technology. Why high quality? Because the temporal resolution of this technology is extremely fast. So functional MRI, as I mentioned earlier, measures every 500 milliseconds to 2 seconds. ECOG could measure neural activities at a level of 1 to 10 milliseconds. This is very important because it is commonly believed our neural activities happen at the order of 10 milliseconds. So 500 milliseconds is way too slow. It's not able to capture individual neural activities. To be able to capture individual neural activities, we have to have faster technology, that is this ECOG. Okay, so we were looking at the data collecting from one epilepsy patient. We asked this patient to perform multiple gambling tasks. So we try to understand how brain works during decision making. So what kind of decision this patient needs to make? We ask him to gamble. We ask him to do a lot of different experiment, gamble games, gamble tasks. These gamble tasks, we have some different sort of features, characteristics for those tasks. One way to categorize these different gambling tasks is some of those belong to high-risk tasks, the other belongs to the low-risk task. So during high-risk gambling games versus low-risk gambling games, we want to see how brain activities are different in terms of this effective connectivity. Okay, we inserted 61 electrodes, particularly placed not in the entire brain, but just focusing on the orbital frontal cortex, because OFC is known to be responsible for human decision making. So this is the area we are particularly interested in, and we measure the data over time. So the data we collect essentially is also a location by time matrix type of data. So we measure it over about 3,000 time points. Okay, so we have 61 electrodes. We have about 3,000 time points. And so that is kind of the data we are looking at, and we want to build an estimate of this effective connectivity network. See how one particular location influence another location. Okay. Of course, this kind of application is not only restricted to neuroimaging, like gene regulatory network analysis or diabetes studies and many other studies. ODE could all be, or similar settings could also arise. And part of the reason for this study, we use ordinary differential equations is also due to this fact that, we collect the data at such high temporal resolution. So we tend to believe we are not interested only in the individual signals, but we are also interested in the derivative of the signals. That is something we are interested in. So that naturally leads to this ordinary differential equations type of models. So XT is our system of, say, p variables of interest. In my example, that corresponds to 61 time series data. We want to model the derivative of this signal as a function of this signal. So that's kind of the backbone of this ordinary differential equations. Okay, and then of course, this signal itself is not something we directly observe. What we observe is a noisy version of that. So we have this measurement error added on top of the latent signal. So we observe this noisy version. And here, for simplicity, we assume this measurement error follows a normal distribution. Yeah, actually, one of the early papers, pioneering work done in this area was by Danina and Ali. I know he's not here today. And you had an earlier paper looking at this type of model, but you are focusing on some particular family of models in this setting. We are kind of extending it to something a bit more flexible, a bit more general. Okay, but kind of similar setting, similar formulation. Okay, so this is a problem we are interested in, and we want to uncover the structure of the system of ODEs in terms of which variable regulate or affect which other variables given this observed noisy time course data. And what do we mean by, say, one node regulates the other is determined by this F function, okay, in this ODE system. So that is something we are targeting. We try to uncover this F function right here. In the literature, of course, people started with a linear model, very natural starting point, and then gradually we start to consider a bit more complicated models. One is this additive ODE, and I believe this 2017 paper was by Danina Ali and Shijie Chen, and then of course it's family which treat these functions f as completely known. Simply put, simply put, what we want to do is we again adopt the same kind of ODE model framework, but we want to estimate this f function in a more sort of flexible way by treating those as some sort of non-parametric functions.
So I know you talked about looking at iris versus, like this is task data. But what you've written has like no, as far as I can tell, like no exogenous inputs. Like unless you're putting the current task condition into X, but presumably like a gamble isn't causing itself. So I'm just curious, like, is there an exogenous input, like I don't know, like a G of T, which is like what the experimenter is doing to the subject that then enters the model somehow?
Yeah. So right now, so first of all, in our model, you're absolutely right. We didn't include this kind of external.
Yeah, it's just like a closed system.
Right. On the other hand, if we have those kind of signals, in the discussion of our paper, we did say this model can accommodate that kind of situation. The single idea is you look at it as XT, you partition it into two parts. One sort of model like in green regions or green nodes, and then we have another part which are the external signals. Here in our model, it's writing all together to one piece.
Yeah, and you just put some constraints on that, right? Like it's take sense of the brain signals to influence like these items input.
Exactly. And right now, because we put it there, all this at one big thing, we do not impose some extra constraints, but we do have the second part is external, they probably treated somewhat differently, then this so this is again the main idea. This is kind of the model framework. Then this is what we are targeting. What's different between our proposal and existing work? Kind of straightforward. Now, of course, the actual estimation problem and the related the inference is not trivial. So the key idea here is we use this reproducing kernel approach. So we say, oh, each function, this f function resides in some reproducing kernel Hilbert space, and we focus on two main components. One is a main function, the other is a two-way interaction. Okay, of course, we can further allow higher order interactions, but in reality, very often we found like a two-way interaction probably reasonable. So we've assumed this kind of a decomposition of the functional space where those f functions reside. Okay, now the second part, or what we mostly propose, we borrow from this reproducing kernel literature. And then we develop some estimation methods, which is again like a two-step approach. First step, because we do not observe the latent signal directly, we come up with an estimate of the latent signal. Then the second part, we want to add this kind of RKHS norms to regularize our estimation. And on top of that, we further add the sparsity. So we want our estimated directed network to be sparse to improve the interpretation. And then we now, again, as I said, it's a relatively straightforward conceptual framework, a bunch of technical details we want to figure out. And after we solve this estimation procedure, we further derive this confidence interval for the estimated trajectory, and we ensure we study the property of this estimated trajectory, the confidence interval of this estimated trajectory, and make sure it has a desired coverage probability. And a few other statistical properties like the convergence rates for the trajectory, convergence rates for the individual functional estimate, and as well as the selection consistency because of the sparsity we impose. Okay, so again, I'm going to skip all those technical parts. Let me jump to the data analysis. Here, those tasks, we divide this into two parts, low risk group and high risk group. This is what we found. Here we enlarge the plot a little bit. We have those 61 electrodes located in this OFC. And what we found was, based on our estimation, the posterior OFC tends to be more more actively influence other nodes during the low risk games, and the anterior OFC tends to more actively influence other nodes during the high risk games. This sort of agrees with our findings from other studies where people found that this again posterior OFC tend to be more responsible when the decision we want to make is relatively simple, but the anterior OFC tend to be much more active when this decision-making involves more calculation, more kind of harder decision. Now, of course, in a simpler, lower risk gambling, relatively easy task, easy decision to make, high risk game, harder type of decision making. Okay. So this is the second example right here. The next example, again, as I said, I'm just going through some high-level description. We switch gear one more time. This is the last topic. Have about 5 minutes, so I'm just going to briefly mention what this is. Now, the third problem also, of course, motivated from our neuroimaging and problems, but it's a classic. The problem itself is just a classical mediation analysis. And I think many of you are experts in this room, are experts on mediation analysis. So this is just a classical setting of a mediation analysis. We have exposure variable. To keep it simple, keep everything simple at the beginning. Suppose there is a single univariate exposure variable, a single outcome variable, and we have multivariate potential mediators. And the goal here is to find out which subset of mediators are really sort of relevant, really important over here. So this is kind of the problem we are targeting. Our motivation came from this study of the Alzheimer's disease. Alzheimer's disease is one of the major application areas or disorder we are looking at. Specifically, we want to understand how amyloid beta affects tau, affects cortical thickness, and finally, the cognitive behavior in the end. So amyloid beta and tau are two well-known pathological proteins in the brain. So these are two types of sort of like toxic proteins in the brain. If we have too much this kind of brains accumulated in the brain around the neurons, they accumulate around the neurons, they first of all would block the communications between neurons, and eventually they would kill the neurons. You can imagine intuitively, if we have too much this kind of waste or toxic proteins accumulated, it's bad. It's going to affect our cognition in the end. So this is kind of the motivation. And one formulation to answer this kind of problem is mediation analysis. So the neuroscientists have some kind of hypothesis. They believe there might be this kind of causal path where this amyloid beta really is a sort of one of the starting points that affects the tau and cortical thickness downstream, and finally affect the downstream cognitive score. So our exposure is amyloid beta here. The outcome, that is our E. The outcome Y is this cognitive measure. More accurately, is a change of some cognitive score between two consecutive visits of the same patient. And then here we have two sets of potential mediators, tau and gray matter cortical thickness. The first comes from the PET image. The second comes from the anatomic MRI. We have multiple subjects, close to be 200 individual subjects. So our question is very simple. I just want to find out which subset of mediators are really important, just like a variable selection. But we put everything in this framework of mediation analysis. Then it turns out this can be a very challenging problem. The main challenge is the number of possible paths that go through all combinations of the mediators is huge. It's super exponential. Okay, and the reason, again, it's easy to see intuitively. If these mediators are all conditionally independent, this problem is much easier to deal with. But we don't want to assume conditional independence. Conditional independence means given the exposure, those different parts of the brain, they should have nothing to do with each other in terms of this mediation analysis. They should be totally independent, uncorrelated with each other, which we do not believe to be true for our brain imaging data. And I do not believe this is true for like genetics type of applications either. Those individual brain regions, individual genes, they are highly correlated with each other, at least some of those, then this conditional independence does not hold. If this conditional independence does not hold, that means among all these potential mediators, there could be all these possible paths. And there will be so many all possible paths. And then makes this problem much harder. Okay. One way to answer this scientific question is just use sparse regression or sparse estimation, which in effect can, to a certain extent, answer this question, which subset of mediators are important. But we all know estimation is not quite the same as inference. Inference means I want to get a p-value. I want to quantify the statistical significance. So we want to be able to develop an inference approach to infer the statistical significance of those individual mediators, while at the same time, we do not want to assume the conditional independence. We want to allow conditional dependence over here. When we first started to work on this problem in 2018, there were only one paper that allowed conditional dependence. All other papers either assume conditional independence or they just ignore this possible conditional dependence. And then turns out, this is a very nice paper, by the way. This paper, they did allow conditional dependence, but their definition of the relevant or important mediator is different from our definition. So in our paper, we give more discussion on why it's different, why we believe our definition is somewhat better. Okay, so that's and as a result, the approach, the inference approach, the test we developed is very different from their test. So I just have a few minutes, maybe not much time left. I'm just going to go through the next few slides very, very quickly, just show you the main ideas. First of all, we measure everything under this Gaussian graphic model. So this is a parametric approach. This testing method we are developing is a parametric approach. We assume this Gaussian linear model or Gaussian graphic model. And then we define what do we mean by the total effect for one particular direct path from the exposure to the outcome. I know all these things look complicated, but in reality, all these things are quite straightforward conceptually. If I have a single mediator, this total effect of a path that is just the product of the effect from the exposure to the mediator and from the mediator to the outcome. This is a classical. All the mediation analysis use this classical definition of the effect of the path. Here we just generalize to multiple mediators. Okay? Conceptually, nothing really fancy. And then how do we define if the mediator is important or not? We basically said, look at all those possible paths that go through this particular mediator. As long as one path has non-zero total effect, we believe this mediator is important. If all paths that go through this mediator has zero total effect, then it's unimportant, irrelevant. Again, I think this is a kind of intuitive definition. Then how to test this hypothesis? We further translate it to something equivalent. And if you look at this equivalent hypothesis, again, conceptually makes a lot of sense. If we think about this, if one mediator is important, that means there has to be a path go from the exposure to the mediator to the outcome. So that means the exposure has to be one of the ancestors of that mediator. And that mediator has to be one of the ancestors of the outcome. Right? That's it. If we think about this conceptually, if one mediator has this non-zero total effect of the one path, then the exposure must be one of the ancestors, and the mediator must be one of the mediators of the outcome. That's essentially what we try to test. And this kind of hypothesis can be formulated by testing, just say, give me whatever mediator, or including the exposure. I just want to see if it belongs to the ancestor set of the rest. That's the translation we did. And then how to test this hypothesis? Our main idea is that we realize we can construct a statistic for this kind of hypothesis based on multiplication of this matrix W. What is W? In this Gaussian graphic model, this W is this gigantic coefficient matrix. So all these possible paths, if you look at them together, essentially is a multiplication of this matrix. Again, this is somewhat intuitive idea, but then we realize it's very difficult to derive this, the limiting distribution of this this test statistic. So we redefine the matrix multiplication, matrix addition operators so that we build a test statistic which is much more tractable in terms of the limiting distribution. So that is our main contribution to redefine this matrix multiplication, matrix addition operator so that we can construct a reasonable test statistic and we can derive its limiting distribution. And on top of that, there are a bunch of other techniques we employ to make this whole thing work, like with data splitting, with screening, and because we are dealing with high dimensional mediators, backstage, involves all these high dimensional regressions. So we use debiased or decorrelated estimator. Finally, we use multiply bootstrap to obtain the critical values and did multiple testing correcting. And in the end, we were able to show that the test we propose has the controllable asymptotic size, has the power approaching 1, and the desired FDR control. Let me just show you these results. This is the studies we started with. Amyloid beta as exposure, the change of cognition as outcome. Here are 2 sets of mediators. So we further modify the test I described earlier. We can infer, we can figure out which paths are really relevant, or in other words, which brain regions these paths go through in terms of tau, in terms of cortical thickness. We map these regions into the brain, which are very interesting findings. Some of the regions are very well-known. Some regions are less well-known, but these paths seem to make quite some sense by my collaborators from the neuroscience. Yeah. I think that's the case studies I want to just talk about. The last few slides, I just show some additional papers, topics we have been working on. I'm not going through all those. If you are interested, I'd be happy to point you to more of those. That's all. Thank you. Please.
So it's case study number 1. So your matrix A,
Mm-hmm.
you have to estimate it, right?
Yes,
so I think of it as a processing step, or I guess so. Right? So you're inheriting the uncertainty of that estimation step.
Right. Yeah, the simple answer is no, we didn't further incorporate the estimation variation here. So we treat it as if it's known. Yeah, but you're absolutely right. Yeah, this is estimated. Yeah, so there could be extra layer of
use a graphical model. We use a graphical model.
Oh, yes, we just use I think we use Gaussian graphical model to explain the covariance and then the precision.
Do you think of integrating the graphical model into your graphical model?
Yeah, in principle we could, just but it would make it much more complicated. Yeah, in principle, yes. This study, I think, when we first started to look at it, but because there were a lot of interest in involved in dynamic and behavioral methods. And then we did also, we tried another thing. We found out this is a reasonable compromise. But we also recognize the field components which are left out. That once you make the potential additional variation from the estimation the first step, which A you mentioned earlier that other complications to what we do.
Very confident. Regarding the treatment of case study. So for instance, the functional model, if you're basically low inferences or especially
Yeah, I think these are defined on the cortex. I think that's cortex regions. Like one functional model is the default mode. And there are two other like auditory network. I don't remember all of this. Yeah, I think most of it.
Okay, so suppose with modern versus the graph on the previous page, I think that so the brain function is not entirely specialized, neither entirely discrete.
Not entirely.
Yeah, not entirely specialized. So, for example, some functions not entirely managed by one single model, but it's neither entirely discrete.
Do you mean some of the modules or regions are excluded?
Yeah.
That could be, yeah, this particular brain atlas we use, it was one of, relatively speaking, it was one of the a comprehensive atlas in the literature. I don't remember all the details. It's quite comprehensive, so it could miss some parts of the information. One of the most comprehensive.
So the last question would be on the time statement. Is not a function of time, but
Yeah. It could be the function of other things, but I mentioned, as I mentioned here, we consider a simplified case. Are you talking about this function? Yeah. We could add the subject label covariates over here. Oh, do you mean shall we add covariates inside here as well? I think we could. Yeah. So I think we could. Again, just to make things more and more complicated. Yeah. Here we are primarily interested in the dynamic behavior of this connecting function. So it seems quite natural for us. If actually we feel maybe a better way to incorporate the subject covariates, like I said, maybe boys, girls, they have different growth patterns, for instance. If that is true, we could add those covariates over here as part of the function of this connecting probability, rather than adding those things here inside this function. I feel that is more manageable. Yeah. Sure. Thank you.